Nossa, sai da frente aí, sai da frente. Essa máquina. Me dá uma máquina aí. Pariu. Transportation. De Okamoto. Okamoto se disfarçando de pessoa normal.
Não, tem que dar desculpa pros caras, só né? Nossa, eu ia falar, cara. Aquela porcaria ali.
I work for Lockheed Martin Aeronautics here in town, and I'm on the C5 technical publication.
I'm Nicholas Mitchell. I also work with Lockheed Aeronautics and the F-22 program. I'm the senior manager for gap frame integration.
Eric Links, Lockheed Martin, F-22 program, software engineer.
I'm Glenn Crandall. I'm a member of the Model Airplane Club where you're going to be flying tomorrow.
And I'm Karen Albrecht. I am the Director of Engineering at Lockheed Martin here in Marietta, Georgia.
I am Daniel Salgado, member of the Keep Flying team from the University of São Paulo, Brazil. This brief presentation will show you the relevant aspects of our project. We follow the project methodology proposed by Rayner, from the conceptual design to the detailed design. Our teams comprise of 70 members from different engineering areas. It's the second time we are here at the Aerodesign East, and our mission, we are supposed to fulfill all the content requirements in order to reach this. We have to design a stable and controllable aircraft, and to develop a very competitive aircraft, we set as a mission goal to surpass the heaviest payload in the previous year. Our challenge is to design an aircraft that can be packed and shipped to the US, and to develop the aircraft in a very in a short time, because we finished the Brazilian project in October. And to find a major sponsor increases time, so we headed for a low budget project. In the conceptual design, we have like the general arrangement of the airplane without giving so much detail. Simple calculations are made and very simple predictions. We search for the constraint analysis, where the general layout of the aircraft is investigated. We search for the minimum wing loading, the required wing loading for the minimum thrust overweight ratio. 5 flight conditions were analyzed. The true constraints were the takeoff runway and the climb gradient. So we noted that very high lift coefficients were required, very low wing loadings, and huge wings about 25 square feet. So this area is almost unattainable. It's impossible to reach within the rows. For the propulsion, we selected tractor configuration because it's more efficient according to Rayner. We have carried several wind tunnel tests in order to find the best propeller. We select this one, the orange one, because it has a higher thrust at all speed ranges. Then, as the constraint analysis shows us that very huge wing areas are required, then we select the monoplanes and the biplanes with low wing to improve ground effect, and with a very high lift coefficient airfoil to increase payload. Then, from our previous experience from the Brazilian project, we decided to use an aft tail due to simplicity, and twin tail and twin tail booms like the P-38 Lightning. And for the landing gear, it's tricycle because it reduces drags at takeoff and it's attached to support increased stiffness. Then, as we headed for a clean design, we used the blended wing body concept because it has a smaller drag. Then we researched for new materials as road-created carbon and glass fiber. We searched for Brazilian woods, Kevlar, and PVC foam. We used in our project Kevlar, plywood, aluminum, PVC foam, and balsa wood. Then the 2 configurations from the conceptual design, the monoplane and biplane, were better analyzed in the preliminary design 1. Here, the conceptual designs are frozen, and we do a better calculation of the plane. Our approach was the synthesis model, that's a multidisciplinary modeling, where the aircraft is modeled with several geometric parameters. Then we wrote a computer code here we should follow the computer code, where the inputs of this computer code are the geometric input, the geometric parameters of the aircraft. So a geometry restriction routine calculates if the aircraft fits into the regulation. If it doesn't, it goes back to the beginning. If it's okay, it goes to an aerodynamics routine where it calculates the drag polar aerodynamic characteristics of the plane. And after that, a stability and counter routine checks if the airplane is stable. If it's not stable, it goes back to the beginning. If it's okay, it goes to the performance routine where it calculates the maximum payload, the maximum gross weight the aircraft can carry in 200 feet. Then it goes to the loads and structure routine where it calculates the airplane empty weight and hence the maximum payload. Then we save the aircraft and it goes back to the beginning and another aircraft can be analyzed. After 100 aircrafts are calculated that way, we go to the optimization takes place. We follow an evolutionary algorithm that simulates the Darwin's theory of evolution. Our approach was the Ramus killer queen, where that population of aircrafts that were calculated that way in the synthesis model, the best aircraft of that population is selected as the queen. And its parameters like aircraft span and the aircraft span and aspect ratio, for example, are mutated to generate new airplanes. Then a new population, optimized population is created. And after 100 generations, we have this is the best airplane from that synthesis model, and after this one's the best aircraft after 100 generations of the optimization. Then we have a selection criteria to check the best airplane inside the optimized population. The selection criteria was payload and climb rate, manufacturer, and reliability. At this point, the designer experience takes place. It's not just the result of the computer. The person must select the best one. Then we go to preliminary design 2, where the best airplane was selected, and recalculated again because all the calculus was made by the computer, and we're going to recheck the calculations. Then aerodynamic analysis takes place to predict drag polar and to investigate the ground effect deeper. Then we use the vortex lattice method and a Pano method, and we found it. We result in the blended wing body final configuration. We found that the ground effect really improves the performance, as you can see in the drag polar. And then a performance analysis, takes place to predict maximum payload, the maneuverability, the climb capability, and to provide data for load analysis. Our methodology was to simulate several flight phases for several payloads and altitudes. We wrote a computer code with 3 degrees of freedom non-linear simulator. Our model scans from the aerodynamic analysis and were refined with avionics. And these are the data for 2,000 feet altitude. And we are expecting to lift about 29.5 pounds in 200 feet. Our goal in the stability and control, the goals are to predict the behavior of the aircraft in flight, to stay on the center of gravity properly, and the counter surface and the servos. We carried static stability analysis, considering the ground effect, dynamic analysis, counters, and a very simplified aeroelastic analysis. And some of the results, for example, that the spiral mode is unstable but acceptable, and we had to relocate the landing gear. Then a load analysis takes place. To design the structure properly, the aircraft must be light but stiff. Then the load analysis is very important. We follow the FAR regulations. We did a VM diagram with a maximum load factor of 2.5 and a minimum of -1.2. The wings loads were calculated for 2 critical conditions in flight and landing. The tail loads are accounted because the tail booms are attached to the spars. The loads were calculated for fuel deflection at maneuver speed, and the landing gears in 1, 2, 3 points with a factor of 2.5. Then, as the blended wing body concept was adopted, the cargo box is located into the wing, so the spar could not pass through it. So 2 spar configurations were selected. One in the front of the cargo box and another in the rear of the cargo box. This spar was selected due to aeroelastic issues. But the front section, center section of the front spar was kept because when the aircraft lands, the vertical loads increased the torsional moment on the rear spar, so the front spar center section was kicked. Then the tailbone truss was, geometry layout was adjusted by topological optimizations, and the tail spar was placed to,
We're at 9 minutes.
okay, to reach maximum counter efficiency. Then at the detailed design, we do the final blueprints of the airplanes, and we calculate we know the maximum payload accurately. We had done 2 prototypes. They had 4 successful flights. One crashed due to the tailbone failure. They were all instrumented with avionics. The aircraft, we conclude that the aircraft stable and flies smoothly. It has acceptable maneuverability. It lifted 25 pounds, and the tailbones were reinforced to ensure that it won't happen again. And these are our final aircraft. All the dimensions summed together do not surpass 175 inches. The aircraft will lift 29.5 pounds. The aircraft costs $650, less than we expected. Then we found that the new materials really reduces weight and cost. The aircraft costs the half of the design value, and the aircraft fulfills the requirements. The project was successful. It's a very competitive aircraft. That's all.
Time.
Any questions?
I have a question. You said one of your goals was sizing of servos. I see you've used extremely small servos. Have you, and you said you've done flight testing, have you seen what modes, top modes your servos can take?
Yeah, actually the servos were designed for the maximum hinge moments at maneuver speed, right? But we didn't have, like, the avionics didn't can measure like the servo forces or the loads on the servos. So as we didn't have any servo problem in flight, we accepted that it was okay. But we just did analytic results.
Let me ask one more quick question. What is the green material?
It's divine cell. It's PVC forward.
Okay.
It's more lighter than balsa.
If you had more time to continue development of the aircraft, what would you change?
What would I change? We would change. We didn't have so much tests, right? Because we didn't have time to do more tests. We think that the aircraft is very good. We will do more tests. In the Brazilian project last year, we done other kinds of tests, like the wing destructive test. We will do more tests, more flights. We would change the aircraft particularly. Maybe the tailbone, because we found in the test flight, that it had a failure. So we reinforced the tailbone. But we will change the table maybe, and we'll do more tests, much more tests.
Can you talk to the trade studies you did for the propulsion system and developing the choice of propellers?
Yeah, we selected the tractor configuration because it gets the airstream flow. The airstream is like cleaner than a pusher configuration, and the propeller selection was done by wind tunnel test. We bought about 20 or 25 different propellers, and we carried the wind tunnel test for different airspeeds to see what propeller would perform best, and we judged that those results are adequate for design purpose. So we have tested several propellers. I don't. It's okay.
What do you believe is the most innovative design you have on your aircraft?
Innovative, the blended wing body, because we never tried this. Our team exists about 5 or 6 years, and every project in Brazil, and we were here in 2007 in the US, and we also every project we say, oh, we can do a blended wing body concept, and nobody had the courage to do that. Oh, it may be risky. We never did something different like that. It may be, if it won't work, we have to change in a hurry, and we won't have time to do a better project. let's do not try anything different. This time we try to innovate because we had a very short development time, but we put all our courage in this. Right? So we find that this is the most innovative thing. And we noticed in the Brazilian project that the ground effect really is beneficial. It's really good for the aircraft. So it's I don't know if other teams know that all of our projects has a very low wing. I think that's the most innovative thing, the blended wing bar concept.
Are there any other questions?
You did talk about the placement of the wing spars. What kind of stress analysis did you do, bending analysis, et cetera?
We carried two analyses, analytical approach, and by a computer program we done with beam elements, and we carried finite element analysis with the spars. But we know that it's important to do computational tests to see what spar configuration is better and if it's really stiff enough and if it will bear the load. But we would like to do tests. We think that tests are as important as design by computer. We think that is.
Thank you. Appreciate it. Thank you very much.
You have 2 minutes to disassemble.
Okay.
And thank you very much.